Welcome to this video tutorial with AI Studio. We're going to start by training a decision tree over the golf dataset. In operators, we search for tree, and the decision tree is the standard algorithm we saw in classes. And to see how good the decision it is, the decision tree, we're going to apply it over a dataset and compute some performance metric. The apply operator applies the model over some dataset, and after applying the model, we need to compute somehow the performance of the results of the predictions. We can do that by using the performance classification operator. That operator receives the label data that the applied model generated by applying the model over a dataset. And this output over here are the performance metrics. Which data are we going to use to apply the model that we train here to measure the performance? In this first case, we're going to use the same data we use for training the model, something we saw in the theoretical part of the course we should never ever do. But we're going to do it with pedagogical purposes. If we run the process, we see that accuracy is 100%. This representation here is what's called a confusion matrix. The columns represent the reality, true, no, true, we don't play, true, yes, true, we play. And this is the prediction of the model. This 5 here means that in 5 cases where the reality is that we did not play, the prediction was indeed that we did play. And this 9 over here means that in 9 cases where the reality is that we did not play, the prediction was that we indeed did not play. In a confusion matrix, the values in the diagonals, they are the times that the model made the right predictions, and the values outside the diagonal, in this case are 0, are the cases where the model did not do the right prediction. We also have here metrics such as the percentage of time we made the right class prediction. This is the decision tree. If we arrange it this way, is the decision tree we cover in the theoretical part of the course. And the performance is 100%. We already know that this is a little bit ridiculous because we only have 14 training instances. The reason why we got 100% is because we are applying the model over the same data we use for training, and this promotes overtraining. If we change a little bit this setup, Ctrl C, Ctrl V to copy all these operators, I'm going to select all those operators. And move them down here. And I'm going to use the split data operator to split my data set. In, for example, 70% for training and 30% for evaluation. And now the 30% for data for evaluation is going to go to the apply model operator. So we use different data for training and for testing the performance. If we run again the process, now we got an accuracy of 50%. We have values outside the diagonal in the confusion matrix. For example, those 2 instances over there were instances where the reality is that we did play the golf game. However, the model predicted that no. So those are 2 mistakes, and those are the 2 times we guessed correctly. We know that one of the drawbacks of this scheme is that if we change the proportion of instances, we can get different results. Even if we maintain constant the proportion of instances in the different partitions and we change the way we generate those partitions, well, again, 50% in this case. However, notice that the errors are different. In this case, we have mostly errors where we didn't play and we predicted we will play. Even maintaining constant the proportions, if I use a different local random seed to make the partitions in a different weight, again 50%, I'm being quite unlucky. 50% again. Probability is conspiring against me, but the reality is that it could be possible, and eventually I will manage to get a different result just by changing the size of the partitions 100%. Okay, this time we got an 100% accuracy. So just by changing the sizes of these partitions or the random number which generates those partitions, I may get different results. I'm going to leave the default results where the guess was that the accuracy was 75% in this case because I'm using a different random seed, but that's the guess, 75%. The best scheme to perform the evaluation, and the one we should use wherever possible, is a cross-fault validation. By default, it uses 10 faults. That means that it's going to train and it's going to test the performance of 10 different models. We will require about 10 more times computing power for the training, therefore, but we're also going to be able to estimate confidence intervals for the metrics that we compute. I'm going to copy those two operators that I will be needing within the nested cross-validation operator. Double click, right click, paste. Over here where we're going to apply the model, and the model is going to be applied over the fault which was left out of the training. The data that's going to come out of that port is the data which was not used to train the model that goes in the first part of the operator. In this part, we're going to get, this is a tenfold cross-validation, the 90% of the data that is used for training. And over here, the 10% of the data that is used for validation. If we go up and output the metrics over there, if we run this process, according to cross-fault validation, the accuracy is 45 plus minus 44. So it's all over the place, and this is quite reasonable because the number of training data I have is too tiny. So I'm not going to really learn anything from the model, compared with 75% over here, 100% over there. This is the more realistic estimate of the true performance of the model. If instead using a toy dataset, too small to learn anything, I use the iris dataset, which despite being small for the complexity of the problem, it has enough training instances to solve the problem reasonably well. So if I feed the iris dataset to these different operators and I run, again, in the cross-fault validation, the performance is more or less 95 plus minus 4%. When I use the training test, the performance was 95.5. It's not very different from the other one. When I train the test over the same dataset, it's overestimating probably the performance. I think it's not far from 99%. In this case, you can see that the confusion matrix has three classes, one per different type of iris flower, and both in the rows and in the columns. And for example, these are three Iris virginica, that was the true class, that were misclassified by the model as Iris versicolor. And these over here are four true Iris versicolor, misclassified as virginica. If I select the decision tree operator, over here we see different configuration options. By default, it uses gain ratio, but we have other options such as information gain, which typically performs work when we have ID-like attributes, or Gini, or I may also use accuracy to measure the purity of the leaves. And I have different pruning options. For example, over here I have the minimum size of the leaf to be after the split, excuse me, this is the minimum size to be split. In this configuration, in order to split a leaf, it must have at least a size of 4 instances. If not, we are not going to try to split it. And after the split, the leaf must contain at least 2 instances. If not, we're going to undo the split. It also has over here a minimum GALE in order to accept the split. If the function we are using to measure the impurity does not decrease by that minimum value, we are not going to do the split. While training decision trees, you may play with those parameters, especially with pruning, but right now I'm going to remove all the pruning in all the cases. I'm going to run again the process. The accuracy of the tenfold cross-validation went down. It went down a little to 94. This makes sense because by applying absolutely no pruning, I'm promoting that the model overtrains over the training data, just memorizes it. This skin didn't change too much. And over here we got 100%. When we allow the tree to grow leaves as thin as it wants over all the data set, and then we test over all the data set again, the decision tree just memorized the data set. This is an example of overtraining. This is probably what's really happening with this decision tree. The performance decreased a little bit because using a little bit of pruning in the decision tree is a good idea. Over here we have one of those decision trees. You can see that is relatively large. If we actually apply pruning, the one we are showing is the first one. If we put back the default values of pruning, the decision tree is much smaller than the original one. Okay, I'm going to remove the first two schemes to testing the performance of the model. I only did this because I wanted to do it for illustrative purposes, but whenever possible, use cross-fault validation. It's better to have a confidence interval, mean plus minus standard deviation for the performance of the model. And I'm going to use different models. We started with the decision tree. The first one we saw in theory, and the next one we saw are rules. The rule induction are the decision rules that we cover in theory. I'm going to output the model over there. Over here, for example, we have the rules. If A3 is less than 2.45, then you are iris setosa, and if not, if this condition is met, you are iris versicolor. And we have another rule over here, and it seems that we are covering 145 out of the 150 instances. A few instances were not covered by these rules. The performance, you want to inspect it, is here. Is 94 plus minus 5%. Seems to be a little bit lower. I say seems because later in the course we'll see exactly how the performance should be assessed. The next model we see is naive Bayes. Over here in the model, if we go to plot view, we can see the 3 Gaussians. Naive Bayes is going to learn a Gaussian for this metric dataset for each of the classes, for each of the attributes. So for the attribute A1, the one we are visualizing over there, the model trained a Gaussian to capture the behavior of this feature for each of the 3 classes. The blue one is Iris setosa, the green one is Iris versicolor, and the red one is Iris virginica. The model has estimated the mean value and the standard deviation of each of the 3 Gaussians. As a matter of fact, if you go here, instead of plot view, that we are plotting the Gaussians, we go here to distribution table, you can see the mean value and the standard deviation for each of the classes, for each of the attributes. In plot view, we can, for example, see that for A3, that we know that that's probably the attribute which best separates the different classes of iris species. Indeed, you can see how the Gaussians are quite separated, especially the one of Iris idosa. These ones do overlap a little bit. A4 is a more or less similar situation, and A2 is where everything is more mixed and there is more overlap in the Gaussians. The model got a 95% accuracy also. There is a version of naive Bayes that instead of training a single Gaussian, it turns a set of Gaussians for each of the classes. It can be useful when you have non-normal distributions and you want to approach it with many normal distributions. By default, it's going to use 10. Excuse me, that's not the 10. This is the 10, the number of kernels. Each of those Gaussians is called kernel. And by default, it's going to use 10 Gaussians to model each of the classes for each of the attributes. You see how, for example, for the red, I have a bunch of peaks, 1, 2, 3, 4, 5, 6, 7. And over here, probably some of these peaks in reality is the sum of different peaks. Each of those Gaussians in reality, or each of those lines of one color in reality is made up of the sum of 10 Gaussians. You may change that parameter. For example, if we use 3, it'll be much more obvious, at least for some of the features. Over here in the blue, you can see very clearly the 3 Gaussians, and also in the green, in the red. If your data, if your attributes are not normally distributed and they seem to have multiple peaks in them, this can be a good option. To use Bayesian networks, you'll have to go to the extension menus, Marketplace, and search over here for Weka. You'll have to install that operator, this one over here. That extension installs within RapidMiner. I need to restart. Okay, I'll restart now. And I'll save the process. That extension installs within AI Studio all the operators which are available in another tool which is called Weka, which is a completely open source tool. So all the operators have been installed in AI Studio. Let's go back to the process. And now you should see that here in operators, you have these extension folders. In that extension folder is where all the new operators are. We have over there a bunch of new different operators. Now we can search again for Bayesian operators, and the W Bayesnet is the Bayesian network operator from Weka. You see that this operator is white. That's because it's a non-native operator within AI Studio and it has less functionality. For example, it's harder to configure. There's less configuration options for these operators. If we run it, in this Weka result, we can see the graph. We can see that by default, this is, this is the prior probability of the class. This is what I show because I click in label by mistake, but this is the class, the label connected with each of the 4 attributes. By clicking on the attributes, we can see, in this case, discrete probability distributions. This operator discretizes all the values of the different features before training the net. This in reality is the same as naive Bayes, just the class connected with all the attributes. The performance was 93%. If we change from KDOS topology K2 topology to TAN3 augmented network topology, and we run it again. Over here we see also the class, the label connected to all the attributes, but we see a tree. The tree, the root is A1, connected to A3, connected to A4, connected to A2. That will be the tree which have been augmented, and now the accuracy is a little bit better, and this topology of network is a little bit more powerful, and it produces a small bump in performance in the model. Another model we cover in theory is K neighbors, K nearest neighbors, KNN. In this operator, we can configure how many neighbors we want to have for each of the instances to be classified as the majority class among those neighbors. By default is 5 neighbors, but we could change that value. We can also change different ways of measuring the neighborhood, which are the 5 closest instances. If we run the process, we got a quite nice accuracy, 96%. It gets a quite good result. The strategy of just looking for closest neighbors of the iris dataset and labeling the classes based on the majority label of the 5 closest neighbors. Another model we covered is neural networks. The neural net is an operator which reflects the more traditional, let's call it like that, neural networks. This is the topology of the network. If I click here, I can see the weights connecting this neuron of the first hidden layer with the 4 features plus the bias. The 3.3 is the bias. This is another bias. Those are the 3 output neurons representing each of the 3 classes, Virginica, Setosa, and Vesicolor. The performance of this neural network was 97%. You can edit the number of layers. For example, this is hidden layer 1, this is just a name, and let's put over there 10 neurons instead of the default value. Hidden layer 2, hidden layer 1. Those again, they are just the names. They are not used for anything else. And let's put a value of 5 over there. This is going to be a more complex network. Performance actually decreased, probably because now I have more parameters. Maybe a little more training cycles may improve the performance, or maybe just is too complex network for this problem. Yeah, now performance is quite close to the previous one. Maybe I should tweak a little bit the parameters. It's also probably the case that this is not a complex problem and I don't really need 2 layers to train the neural network. The auto multi-layer perceptron is also a neural network which will attempt automatically to decide how many layers, how many neurons to use. It's a fine operator, you may play with it. And the deep learning is a neural network more close to the deep learning neural networks, the more current neural networks. Here, for example, we can choose between different options for the activation function. The hyperbolic tangent, the rectifier is the ReLU function. This is the exponential rectified linear unit function. The ones with the dropout, they will allow us to specify a certain percentage of dropout. And over here, we will have to put the dropout for each of the layers. The exponential linear unit is a fine choice. Over here, we can decide how many neurons in each layer do you want. 50 is probably overkill for this problem. Let's go for 2 layers of 20, and that should be more than enough. This is the number of epochs to train the data. There are not too many, honestly. Let's see what happens with that default value. And over here, we have other parameters such as values for regularization. By default, this operator also imputes using the mean imputation, although there's also the option not to do anything, but by default uses mean imputation if it sees a missing value. This operator by default also numerizes any nominal attribute. The neural net does not numerize, but this one does. If we run this process, performance was not that good, 91%. This is a very small number of epochs, honestly. We need a much larger number in order to try a neural network of this size. Now we are to a performance quite similar to the standard neural network, around 97%. This training samples per iteration is the batch size, by the way. -2 means that it will be determined automatically, but you can override it. You can decide, for example, that our batch size is going to be 16. I don't know what default value it uses, but 16 could be a fine value for this problem. And we got a little bit less performance. So the default value was a little bit better than my value. Honestly, if I wanted more performance, I would probably decrease the size of those of the net, and maybe also decrease the batch size, because after all the data set is small, and this could lead to a model with a little bit more performance, about the same as the same time, close to 97%. And the last model I'm going to try is a support vector machine, which is not the last one we cover in the course, but I left it to the end on purpose. Because if I try to run this model over this dataset, I of course going to get an error, insufficient capability. Why? Because support vector machines can only be applied to binary classification problems. They are just a hyperplane dividing the feature space on what's above and below the hyperplane. And over here we have 3 different types of iris species. If we really wanted to use a support vector machine, maybe we can turn this problem into 3 different problems, differentiate Iris virginica from the other 2 species, and we will train one support vector machine to that task and differentiate Iris versicolor from virginica and setosa, and Iris setosa from virginica and visicolor. And overall, we will be training 3 different support vector machines. In order to see how to use that operator, in order to be able to run it, I'm going to use some binary classification problem. The GALT dataset, for example. This is a binary classification problem, which, by the way, I won't be able to run either, of course, because it has nominal attributes. This can be fixed easily using the nominal to numerical operator using numerization that is going to be applied to all the attributes. And now I can indeed train the support vector machine over this problem. We got a very low accuracy, but again, we know that we have too few instances to actually learn anything useful in this problem. With this, we are done with classification, but we're going to drag the polynomial data the first time we drag it, and we're going to work now on regression. I'm going to run the process despite it will fail, because this setup doesn't make any sense for our regression problem. I just ran it so I can actually show the dataset now. This dataset has 5 metric attributes and a label, which is a class. If you visualize the dataset, you will see that there is no clear regularity in this dataset. We are using the label to color the instances. Those are the scatter plots. and there is no very clear pattern about the magnitude, the color, and the different scatter plots. Lower regions tend to be more blue, but it's quite unclear what's the relationship between the class and the attributes. One of the operators we saw that can be used to predict a metric class is, of course, a linear regression. Besides using an operator which can predict a metric class, we also have to replace this operator because that was used to compute accuracy. Accuracy makes no sense in a regression problem. I want to compute how close I am to the metric class. It's not necessary that I get exactly the right number. If I predict that the value of a stock is going to be 98 and in reality was 97.9, I was very close and it's a good prediction. So I don't need to be exactly, guess exactly the value of the class. I just want to be close. So using the rod mean square error, over here I have more options, by the way. I forgot to show them, but over here in the performance operator, you can also output classification error, kappa, that as we'll see later in the course is quite useful in the classes are imbalances, and you have other metrics that you can also output. We here by default uses the root mean square error, but you may also show the absolute error or the relative error or other options. In the linear regression operator, we can use rich regularization. It doesn't allow to use lasso or elastic neck. That's the functionality which is available in this operator. There is no good reason why they wouldn't allow other. And by default, it uses some feature selection. I'm going to ignore the feature selection, but this means that it's not going to use all the features for the regression. This is a linear regression. There is a nonlinear regression, by the way. Which is this polynomial regression over here, which will compute polynomial features, nonlinear features. Okay, it's not happy because this was not connected to the first output. This is the linear regression we created. The linear regression is 31 multiplied by A1 plus 42 multiplied by A2 plus 27 multiplied by this other attribute and so on. And this is the performance. The error is 79 plus minus 17. So we got an error of almost 80. Let's change the model by another model which is capable of predicting a metric class, which are neural network. Neural networks could be used to predict metric and non-metric classes. By leaving the default operator, I didn't change anything. We got a performance of 36. Much better performance than in the previous case. We could also use the deep learning neural network to predict the metric class. Which got a higher error, 50. And then I should probably tweak the parameters. 50 neurons is very likely too many neurons for this problem. I don't have a lot of data. 10 epochs is too few epochs. And this error was better than with the neural network. These parameters make more sense. It's an error of 23. By the way, with this operator, if you actually had a larger data set, or we will specify a very complex, a very costly training. Let's suppose that instead 300, I'm going to use 3000 epochs. You'll see a clock here showing the progress. Now it's going to take a little bit of time because it's performing 3000 different training cycles per fault of the cross-fault validation. And the error actually improved even better. So the neural network benefited from the additional training. If the training takes way too much time, you'll see the clock going too slow. And if it's too slow, especially if you are just exploring a little bit different options to see which predictive model seems to work the best, use sampling. Okay, you could decrease the size of the data set using the sampling operator, and if I get instead 100%, 30%, it means that the training is going to go faster because it's less data. In this case, it was not necessary, and this probably means I get higher errors because I don't have too much data. But if your data set is too large, or you just want to try quickly a few models to see which ones are more promising, you can use this strategy. And if you see that indeed the deep learning neural network is a good operator and you want to complete a complete training, you may go for lunch and leave the laptop or the computer running a couple of hours if needed to train the neural network with more data or with more epochs. And that's everything for this video tutorial. See you in the next one.